Hello, this talk is about subversion-resistant quasi-adaptive NIZK and applications to modular zk-SNARK. I am Behzad, and this is a joint work with Daniel Slamanig from AIT Austrian Institute of Technology. The motivation of this work is about investigating quasi-adaptive NIZK or quasi-adaptive non-interactive zero-knowledge argument, which is a variant of NIZK where the CRS or the common reference string depends on some language parameter rho of some statement. And which such dependency brings some of the CRS model, brings some allows one to construct a more efficient NIZK for linear language or algebraic language under some standard assumptions. As an application, this quantity has been used in several constructions, like as commitment scheme, IVE signatures, and star compilers. One of the main challenges of this setting, by this setting, I mean in the CRS model, where one needs to assert trusted party, which is a CRS generator, and share this CRS to the parties. And the question is the security of the protocol guarantees if the prover does not trust to the CRS generator, or what happened to the security? This is one thing that we are going to focus on this as a part of the contribution of this paper. And another thing is that in the real world application of the quasi-adaptive NIZK or NIZK, the fact is that the adversary sees many different proofs of the valid prover. And the question is this construction secure, or soundness holds if the adversary sees many proofs? So what if adversary use these proofs and to generate, to mount the proof, or to generate a fake proof for a fake statement? Which, in this case, the adversary might be possible to construct a fake proof for a valid word X, for the same word X which is already queried, or it might be able to construct a valid proof of pi for a different word X prime, which the first one is a weak simulation sound, and the second one is a strong simulation sound. So now the main question is how we can attach this property, I mean simulation sound property, to such quantity constructions. Before we go to our result, I will start with some preliminaries. We first start with the definition of non-interactive zero knowledge in the common reference string model, or in short, NIZK in the CRS model. In such a model, we assume that there is a trusted third party who generates some public parameter, which is or CRS or common reference string, and share is to prover and verifier. And then prover wants to convince the verifier of some validity of some statement X by having the CRS. And prover, using the CRS and the word and proof, checks the claim of the prover and either reject or accept. Such a construction should satisfy the following properties. First is called completeness, which says that for a valid word X or for a valid prover, verifier always should accept the proof. And the soundness is the opposite, says that for an invalid prover or for an invalid word, verifier always should reject the proof. And the last one is called zero knowledge, which says that P leaks nothing behind the fact that X is in the language to the verifier, or the proof of I should not leak any information of the witness beside the fact that X is in the language. But there is another property which is used in the real world application of such construction. It's called simulation extractability, which to get the definition of the simulation extractability, we first start from the soundness to a variant of the soundness is called knowledge sound, which in this case, I mean in the knowledge sound, it guarantees soundness plus giving the guarantees that verifier knows prover knows the witness. So it means that if the prover passed the verification, we can construct an efficient extractor that extract the witness. So in order to construct knowledge sound, we usually use two ways. The first one is black box way. In short, in this case, we force prover to, beside the proof, a pi, he also needs to encrypt his witness with some public key encryption. And then in the proof of knowledge sound, we give the secret key of the encryption to the extractor, and then he can simply decrypt it and get the witness. But the problem with that case is that when we add the encryption of the witness as a part of the proof, then we are somehow increasing the length of the proof, and we make it dependent to the length of the length of the witness. Another way to get knowledge sound is used some non-falsifiable assumption or knowledge assumptions, which is used in some SNARK or succinct non-interactive argument of knowledge constructions, which is based on some non-falsifiable assumption, and, or roughly speaking, it's run on some hard assumption in a way that we force prover to compute, let's say, for example, if we say DL is hard, we say if prover can compute g to the power x in both groups, g1 and g2, then he knows x. This is a simple knowledge assumptions, but we will look at it with more details. In this talk, we will mainly focus on the non-black box way. And then how to go from soundness to the simulation sound. We say that the difference here is that in the simulation sound, we allow adversary or malicious prover to query with many proofs, and later we ask him to produce a proof which is not queried before. And so the combination of simulation sound and knowledge sound gives us simulation extractable or simulation extractability. A variant of NIZK, as I mentioned before, is called quasi-adaptive NIZK, which this quasi-adaptive part comes from the fact that the CRS depends to some language parameter role, which is chosen before the CRS. And it has several applications as a commitment scheme, IB, and signature. And the difference here with the normal NIZK is that one can construct this quasi-adaptive NIZK only for algebraic language or linear languages, which by linear languages, I mean here, the language, the statement depends on, is a linear combination of the witness and some language parameters. The story of QA-NIZK started by Roy and Yulta in Asia Crypt 13, and then ended by Kills and V, which gives the most efficient QA-NIZK, which the proof size only contains one group element. And this talk, we are gonna work on this Kills and V constructions. And we saw that quasi-adaptive NIZK and NIZK mainly was in the CRS model where one needs to trust to the CRS generators. But later, Belare et al. Defined a new notation of the security. It's called subversion security, which they investigated such a NIZK in a way that what happened if neither prover and verifier don't want trust to the CRS generator. Then they defined a variant of zero knowledge. It's called Subversion ZK, where ZK holds even if CRS generator is malicious. Then in that part, both verifier and CRS generator can be one party, for example. And Subversion Soundness, which says that soundness holds even CRS generator is malicious. In that case, from a verifier point of view, both prover and CRS generator can be one party. And then they give several impossibility and possibility results, which the main one is that having both property, I mean, subversion soundness and subversion zero knowledge is impossible. But they say that subversion zero knowledge and soundness is possible, which this property investigated for the zk-SNARK or succinct non-interactive argument for in two works in Asia Crypt 17 and PKC 18. But for quasi-adaptive NIZK, this work is investigated by Abdolmaleki et al., which they constructed Subversion ZK QA-NIZK in a way that both language parameter and CRS are subverted. But still, this is left to see if we can construct Subversion ZK of the QA-NIZK, which only CRS is subverted, and also can we construct this QA-NIZK in the asymmetric model. I mean, in the subversion setting as well, which these two things is gonna be, which some of our contribution of this paper covers these two open problems. And now, as an our result, we first start with the quasi-adaptive of the quasi-adaptive NIZK of QA Eurogroup 15. But before that, let's have a quick recall of some preliminary for this case. Let's see G1 and G2 and GT are an adaptive groups for the P. By notation of bracket of A and this I, we mean A times the group generator GI. And there is a pairing, and there is a map between G1 and G2 to the GT in bilinear map. And by this notation, we mean pairing A and B is AB in group T. As I mentioned, the most efficient QA-NIZK by QA is known for subspace language, also for linear languages, in a way that we fix the language parameter rho in group in exponent, and then the goal is to give a zero knowledge proof for this statement, which Y is a linear combination of some public parameter M in group times some witness X. But this is in the CRS model, which there is a trusted third party who shares this CRS to two parties. And our first result is to see if we can convert it, if we can translate it in a subversion setting in a way that prover does not need to trust the CRS generator. So to design we equip prover with some new algorithm, which is called VCRS or verifying CRS algorithm. Or precisely, we first start with the QA-NIZK, which is in the CRS model. And we add some new elements in the CRS to make the CRS publicly verifiable. I would say here, I would note that adding new elements, one needs to do it more with more care, because it might affect to the soundness property. So we needed to, by adding some new element in the CRS, one needs to also reprove the soundness. And then we designed a new algorithm, which is called VSCRS, or verifying CRS, for checking the well-formedness of the CRS. Or more precisely, this new algorithm takes some language parameter rho, which comes from some correct distribution, and a CRS, which comes from some malicious CRS generator, and checks the well-formedness of it. And if it passed, if it outputs 1, it means that CRS is well-formed. So it guarantees that there is some trapdoor TC. So there exists some trapdoor TC. Then improving, which is very useful to prove subversion zero knowledge. In subversion zero knowledge, we first check the well-formedness of the CRS, and if the CRS is well-formed, or if the CRS passed the new algorithm of VSCRS, then we are able to extract the trapdoor by some efficient extractor, and then pass this trapdoor, this TC, to the simulator in the zero knowledge proof to generate the proof. And we construct such an efficient extractor based on some well-known non-falsifiable assumption, which is called BDH knowledge assumption, which in short, it is somehow says that if given two generator of G1 and G2, if one can generate G1 power X and G2 power X, then it guarantees that the one who generated this thing knows X. So this is some kind of non-falsifiable assumptions. And as a second result, we investigated how we can attach this simulation extractability in this new in this QA-NIZK in the Subversion ZK setting. And we achieved true simulation extractability for Subversion ZK QA-NIZK. By true simulation extractability here, we mean that this is a variant of simulation extractability in a way that the adversary is allowed to query only for some valid statements. But in the standard case, the adversary is also allowed to even queries for some invalid statements. And in both cases, adversary must produce proof which is not queried before and for some invalid statements. And also, we observe that this technique can be applied also for the QA-NIZK of QA, even in the CRS model. So we constructed both through simulation extractable Subversion ZK QA-NIZK and also through simulation extractable QA-NIZK of the QA. And with more details, how we managed to construct such things. In this case, we start with the simulation sound QA-NIZK of QA, which is different from the previous construction. Previous one was only QA-NIZK, but here is simulation sound QA-NIZK in the CRS model. And we also add here, we again use the same techniques and add some new elements in the CRS in a way that still Soundness holds. But here, the CRS, I would again repeat it that the CRS here differs with the previous CRS of the QA-NIZK. So CRS here is different. So for sure, the new algorithm that here we constructed, I mean, this VSCRS differs from the previous one. And again, we constructed this new algorithm VCR in order to check the performance of the CRS, which is gonna be used to prove Subversion ZK in a way that if the CRS that is generated by some malicious CRS generator pass these algorithms, then we are able to construct an efficient extractor by using again some non-falsifiable assumption. Again, here we managed to use this well-known assumption, BDH assumptions, to extract it to prove the Subversion ZK. But here we step more, and we also used discrete log assumptions in symmetric binary group in AGM, and then prove how we can achieve this true simulation extractability for such Subversion ZK QA-NIZK. And some other results, which due to lack of the time, unfortunately, I will not be able to go through to this result. First is analyzing symmetric QA-NIZK of Gonzalez, Asia group 15, which was in the CRS model, and we show how we can get it in the Subversion ZK setting, again, in a way that prover does not need to trust to the CRS, but still ZK holds by using adding new technique, adding new elements, and defining a new algorithm at VCR. And one of the interesting results is that we managed to somehow to integrate our new Subversion QA-NIZK into Lego SNARK toolbox, which before this work it was not considered. So the good thing is that now by having this Subversion Quasi-Adaptive NIZK together with some Subversion zk-SNARKs, one can somehow represent an important step towards to get Subversion variant of Lego SNARKs, which this is, I think, is a nice result. But as an open problem, still it is left to get quasi-adaptive with standard simulation extractability. In this case, so I mean, by standard, I mean, again, I repeated that here in our construction, it was through simulation that in the proof, adversary is allowed to only query it for a simulated proof for some valid statement, but here adversary is allowed to even query it for some invalid statement and get proof on top of that. And also having this property for Subversion ZK is also an open problem. So thank you so much and see you in the main conference.